So I'm excited to introduce Matt and Simon as they're here to talk about their infrastructure. So please welcome them to the stage.
Hi, my name's Simon, this is Matt. We're on Twitter if you want to send us any feedback. Right, if I had to sum up our roles at Monzo, it'd be something like this. I do infrastructure, Terraform, and Matt does that as well as distributed systems engineering. Or if you don't think that reference is any good, this one might make sense too. Right, so we're building a current account, we're building a new bank. Can I get a quick show of hands? Who's already got a Monzo card? Okay, so about half of you, so we've still got a bit of work to go. A bit of context for you. We started about 3 years ago when the government sort of noticed that there weren't as many banks as there used to be. And they changed the rules to make it a little bit easier to get a banking license. So we spent about 2 years after applying for a banking license, did all the paperwork, and about 3 months ago, I guess, we got our full banking license. They don't actually look like this. It actually just looks like a PDF on the Bank of England's website. Super disappointing, but we had a big party anyway. And like I've worked in a couple of banks before I came to Monzo, and the thing that I remember from when I worked in those banks was IT infrastructure of big banks tends to be lots of vendor products that are put together by vendors over a 2-year period with a 2-week warranty period, and then like immediately they put them live into production, they start planning for their replacement. And we wanted to do something a little bit different with Monzo. So I'm really, really proud of this graph. This is the number of banks running entirely free software from the history, from the Big Bang until now. And by free, I mean the Richard Stallman version of free, as in we have the source code for everything from the Linux kernel through the Kubernetes scheduler, all of the source code that we've written Go microservices, as well as the HashiCorp open source software that we use, as well as Cassandra, RabbitMQ. We have the source code for everything. So we're never stuck in a situation where there's a vendor that hasn't got or is unwilling to implement a feature that we want. And by entirely, I mean almost entirely. We do have to run one piece of IBM messaging software, which unfortunately is how all of the banks in the UK talk to each other. But we have a plan to replace that when they will let us. So this was a great opportunity for us in the last 2 years. When Go came along, I think everybody here probably does DevOps. And you know, a couple of years ago, it was all about Ruby. It was about container, config management, Chef, Puppet. Then Go came along and sort of the DevOps community went, cool, let's rebuild everything from scratch. So that's sort of, it's very similar to what we've done. We've decided to sort of build everything on a clean, consistent code base. So it's all in Go, it's all very similar. Hands up if you work for a bank right now. Okay, so there's a few of you, and you probably know the really horrible change management software and change management processes. We've managed to convince management that we should just be allowed to use Git as our change management system. And we've extended that all the way through even things like plugging and unplugging servers in our little data centers. We have a Git repo that reflects those changes, so we're really happy with that. And everything we're building is sort of real-time and API. There's no batch processes. There's no end-of-day batch or anything like that. We love Go. We really like how it's very correct, it's performant, it's lean. Those of you who did DevOps know it's so much nicer now being able to take a small 12 megabyte binary and throw it in a container. No more shipping around 1.2 gigabyte Java WAR files. So we're really happy with that. But we didn't get it right first time. I think nobody does. We started with Mesos and RabbitMQ and CloudFormation, and I remember one day I was trying to do a CloudFormation change, and my finger was hovering over the click button, and I was like, I have no idea if clicking this button is going to destroy my production infrastructure or not. I just don't know. And that was like the point at which we started looking and thinking like there must be a better way, and then Terraform came along. And it was around Terraform 0.6 that we got involved. And I was going to talk a little bit about Terraform, but Nikki pretty much nailed exactly my experiences with Terraform. We started with sort of one Terraform file, and we've gone through the same evolution that Nikki described. And we've ended up in, I think, like phase 5 or 4 of her description. So we use remote state, and we're pretty happy with it. And every time a new version of Terraform comes out, like I get a big grin and I'm giddy with happiness, especially the conditional stuff, which was a big pain point for us. Our Terraform config looks pretty much like you'd expect. We have environments separated and we use modules, and you can see our modules here. There's not really that much I can say about it. It's not particularly special. It just gets on and works pretty well. We're also huge fans of HashiCorp Vault. Like, if you work in a bank, there are some very, very important secrets, and those secrets directly correlate with the ability to steal money. So we're in the process of moving all of our secrets and centralizing on Vault. And we're still in an early stage with that. But one thing I do really like is the ability to use the AWS EC2, I don't know what it's called, the authentication backend. So you can trust that it is an actual machine with an actual AMI that is authenticating against the vault. And that gives us a lot of confidence to store secrets there without having to sort of exchange tokens and keys around. But we are moving toward a more sophisticated setup for our vault, which we're working on at the moment. So we're moving to a setup that looks a bit like this. This bit here, those of you who have good eyesight and read very quickly, you'll notice that we've got Cassandra connected as a storage backend to Vault. That doesn't exist yet, but I'm pleased to announce that Monzo has sent a pull request to contribute that back to Vault. So we're hoping to get that merged pretty soon. The other thing that we do that's quite different to a lot of DevOps shops is we actually treat the building of our binaries, we actually treat the building of our application source code as a critical production function. So where a lot of companies will have sort of a build server or they build using Jenkins, we actually build right in our production Kubernetes cluster. So we consider the workload of building secure binaries to be a production workload, and we've actually moved that straight into our Kubernetes cluster. So we have a command line tool called the CLI, which gives you access to our API. Those of you who have Monzo cards know that everything that you do, you can access through the API. We have more things that we can access through the API if you're a Monzo developer. One of those is you can actually build and deploy our applications, or build and soon deploy our applications. With that, I'm going to hand it over to Matt, who's going to talk a little bit about what we're actually building.
So as Simon mentioned, we have a microservice platform that's pretty much entirely written in Go. It's probably like 99% Go. And that means that we can pick the right tool for the job. In most of those cases, we're doing relatively simple RPC kind of calls between services. So our infrastructure is made up of a very large number of discrete services that all communicate to each other, share one kind of single responsibility, and that means they're really simple. So it's nice and easy for me as a developer to go along and understand what this particular piece of software is doing, especially if I need to make a change to it. Now, that number of services has kind of rapidly spiraled out of control. So we started off in February 2 years ago, and gradually as we built up our core banking system and we've integrated with various number of payment schemes, added all sorts of emoji-based functionality, we've kind of added progressively more services. And that means that you end up with a system that is progressively more complex. And there's no way that I, as an individual developer, will be able to understand how our entire system works. And that's also quite unrealistic if you're building a system which is extremely complicated. Like if we end up with a couple of hundred engineers, one person will never understand how every system works. But that's okay. Within our services, they will communicate over a number of different message buses, either direct point-to-point HTTP or via like a kind of event-based pub subsystem. So if a request comes in from our API, that will kind of fan out to a number of different services, which will then process that type of request. In our infrastructure, the interesting thing is how we communicate between these. So as I mentioned, they're all kind of Go binaries. They're very simple HTTP servers. And they communicate, one service will fan out to a number of services. So for resilience and redundancy, we run a number of copies of each one. A service needs to kind of know which one to communicate to. We do that over HTTP. And when you're doing this in a very large, complicated infrastructure, you need to deal with a huge number of different things. So we do this using Linkerd, which is a kind of layer 7 proxy. It understands the requests that we're making between these services. And all of these things integrate with various different variety of service discovery systems. So if anyone's used Console as a service discovery mechanism, Linkerd will integrate with that, and it will track the locations of all your applications, feed that into the Linkerd binary, and then it has a load balancer built in which will preferentially select the most available and fastest instance of a service that you can connect to. In our case, we run everything in Kubernetes, so we actually use the Kubernetes API to do this, but ultimately it's still kind of the same. So that's all well and good. And then within our infrastructure, if we're making a request between these, we have a number of hosts, a number of services that are spread across all of these. And to communicate, for example, from one service to another service, we'll send a request proxied via a local Linkerd instance, which kind of aggregates all of the traffic, fans that out directly to the remote Linkerd, which then fans it into the correct service. So that gives us a much higher guarantee of uptime. We can tolerate slow instances. If you have instances in Amazon that are particularly highly loaded, all of this kind of will deal with that. So that's great if you've built all of your services in Amazon or in a cloud provider and you kind of control all your infrastructure. However, we need to connect as a bank with a large number of external providers. And most of these people do not have like an API that you can call. For example, you can't send a faster payment in the UK by like hooking up to the faster payment network and hitting that with some JSON. It'd be great if you could. So in our case, we end up with an interesting problem where we have Amazon on one side and we have a variety of different payment schemes and other providers on the other side. And we have to work out how on earth we connect to them. Ultimately, these people will give you some fiber, and there's no way to put that into Amazon. So we have to like build a way to do that. And this is where we found a couple of other HashiCorp tools, such as Packet and Vagrant, to be super, super useful for us. So we have a physical data center. That cable goes into the faster payment network. So my laptop's plugged into there. We're just testing the connectivity. And ultimately, we've ended up with two data centers, which we have to physically rack gear in, which is not something I thought I'd be doing at this stage of my career. But we end up with these, and through them, we can connect to all of our payment systems. We have two for resilience, and then within these, we need to ensure kind of a safe, reliable network path. So in the case that normal operation, we'd probably pass it all through one of them, and then if there's some kind of network failure, we would hope that it would be routed automatically by the second one. And the way we can do this, if anyone's super interested in networking, is with BGP. So we can broadcast BGP from in Amazon all the way through, and then if one of our routes fails, we'll automatically move our traffic over through the other one. And that convergence time is really, really fast. So how does any of HashiCorp's tools fit into this? We initially wanted to create VPNs from our physical infrastructure into Amazon. So we bought some extremely expensive VPN devices. I'm sure someone in this room has probably been in a similar situation. Anyone? Yeah, maybe. And they're really good, but the trouble Simon mentioned is you have kind of extremely proprietary technology that you cannot modify at all, and if it doesn't do everything you need it to do, then you end up with an extremely heavy paperweight that is sat there and doesn't do anything. And that's the position that we found ourselves in. We run everything in Kubernetes, and if anyone's used Kubernetes, you have an overlay network inside that, so you have an IP space that is not addressable from your co-location facility. So you already have quite a complicated network setup. If you're using Calico or something like that, then you have network policies, so you can define all of those in the Kubernetes kind of in your infrastructure, and then your network policies are enforced. So we're trying to establish a connection from an IP that can't be addressed down to a data center, and then off into a number of payment schemes. So the way that we've done this is by firing up some Kubernetes pods, and trying to establish a VPN down to our physical devices. And that doesn't really work. So we couldn't get that to work at all with a number of different hardware providers and lots of support. And it's just not something that is the kind of very slow-moving network world is really geared up for. So instead, we have a bit of a problem. So Vagrant steps in to save the day. We need to model quite a complex setup, and we need to do that with quite rapid iteration. So I can do this on my laptop. I can fire up a kind of basic network. Within that, I then need a number of machines. So Vagrant allows you to do multiple VMs. You can also, if you're using something like the VMware provider, you can get a plugin for that, and then that allows you to do relatively advanced networking. So we can define a number of networks in Vagrant, and then within that network, we can fire up a couple of machines. And within this, we can then test how we're going to configure those. So in our case, we need these to kind of communicate to each other, and they need to appear as one highly available unit that things both in Amazon can connect to, and also our third-party suppliers can connect back to and establish connections through. So we need things like floating IPs. We have multiple VLANs for segregation. These things have to float. We have to be able to test what happens in all the various different failure modes. If we just drop all the traffic on one of the machines, do the IPs fail over to the other one? And we can do all of that on my laptop, the laptop right here. So I can test all of that And we've ended up building a kind of Linux HA system, which if anyone's used things like ChorusSync and Pacemaker, you can set up resource groups with floating IPs, and then we can terminate one of the machines and the IPs will fail over automatically. So once we've built a system like this, we then end up with some configuration that we've tested and we know works, but we need to reliably get that into some machines that are an annoyingly far away. But if I break them, which I have done on more than one occasion, I have to drive to a data center to fix. So I'd like to do that super reliably. And Packer, in this case, is a perfect way of doing that. We've already got all the configuration in Vagrant. We can easily make that into a Packer image. So we can take our configuration we already have. We can wrap that up and build a Packer image. And then from that, we need some way to get this onto our remote machine. Now, in a number of cloud providers, you have a way of, you can build AMIs, and you can push those up, and then you can spin machines up. In the case of building physical machines, that's slightly trickier. You have to get a disk image onto a running machine and re-image it, which is possible. There are many, many ways you can do that. But if you mess it up slightly, then you end up with a machine that doesn't boot anymore. So in our case, we looked at how we could do this. And if anyone's used CoreOS works on a kind of A-B partition, and it'll upgrade itself automatically. So if it's running in partition A, then it becomes eligible for an update. It will lock every CoreOS instance in that region using a locksmith service, and then upgrades the B partition, flips over to it, and if that works, it stays there, and if not, it fails back to the A partition and tries again. So CoreOS has all of this open source. We can reproduce the very small part of that we need. So we end up with kind of like boot partition and A and B partitions. And then with our Packer image, we can build all this, and then we can run a script. We can image at a block level at one of those partitions. So we've got our active and our standby. So it's currently running in the active partition. We've already got an image that we've built. We can fire that over the network, and we want to upgrade our standby to the new version. We write that just with DD onto the disk, and then run a script which flips the boot flags, so that the next time we reboot that machine, it will boot into the standby, effectively making the standby become the active partition. So we can run through all of that, and we've been able to do that in the space of a few weeks. We can build very reliable models using Vagrant. We can then image those and reproducibly create images, which we can then use to remotely upgrade servers in our data centers. And then, as a result, we now have a HA VPN appliance that has cost a fraction of the amount of money that a large provider would cost us. Also, it's something that now we've been through that process, we understand how it works. So as a team, we have the experience, and I know a lot more about networking now than I did a few weeks ago, and I wish I didn't know all of that about networking. But it's something that as a team, we've been able to build up that experience, and that's extremely valuable given that this is the kind of infrastructure we're having to support. The advantage of all of that is that we can take this relatively complicated diagram, which ultimately has, say, a service that sends a faster payment, and that sits in an overlay network in Kubernetes and uses UDP encapsulation to get to the connectivity pod, and then fires that through two different things to get over to the faster payment network. And we can simplify all of that down to an arrow so that anyone else who needs to work on the faster payment service doesn't really need to worry about how that works.
So this gives you a bit of an overview of some of the cool stuff that we've done with HashiCorp tools. We build our infrastructure with Terraform. Terraform's used to launch the CoreOS machines with Kubernetes. We're moving to using Vault for all of our security. Like Matt said, we develop our physical infrastructure with Vagrant and deploy it with Packer. And when it all works, it looks something like this.
Very first withdrawal ever on a Monzo debit card for the Monzo processor. So let's try it. This may or may not work. It failed all the other times.
Why does it have to be raining?
2, 3, 4.
Shouldn't say that.
Cash with receipt. £10. It works. Yes. Woohoo!
So we can see there
Yeah, that was a fun day.
So we can see there that you actually saw the push notification come significantly before the cache actually came out of the machine. It turns out it's really easy to race push notifications through the internet compared to the kind of variety of different acquiring banks and things that card messages have to go through. But at the end of that, we've been able to really quickly deploy systems that work in the real world, that give people money that they can use, and it goes through relatively complicated infrastructure, but using the variety of tools that HashiCorp's given us, we've been able to kind of simplify that.
Yeah, so like I'm not sure everyone says this, but we're hiring. If you want to work on something that half the people in this room use and you would use every day, then hit us up or come and find us. Like half the team's here. So yeah, thank you.